Hello, welcome to Bedroom Builds at the From Python to Rust series, episode number 30, HTTP clients, continuing from the previous episode where we spoke about JSON. There are two ways of using HTTP clients. One would be using the standard known way of blocking clients. So what I'm going to show today is the standard libraries URL lib in Python. And then for Rust, there is a crate called ureg, or I guess a mu request, so micro request. These only implement a blocking type client. And then I'm also going to show how we do this asynchronously. So in Python, for example, you can use the library AIO HTTP. And in Rust, the request by default is async. And it offers a blocking API, but by the default version will work with Tokyo and asynchronous calling. The API I'll be using can be found here. It's a freely accessible API that generates random data about the persons and returns us JSON. So we can then play with this. All right, let's hop over to the code. On the left, as usual, we have the Python code. On the right, we have the Rust code. The Rust code, you can ignore this top section for now. This is just an example of how to decode JSON in a more specific manner. We will first look at this loop starting here. So on the left in Python, we use the URL lib request to do our blocking requests. We use JSON to decode the stuff that's coming back, and we use time to know how long all of this takes. And then I created a central small module called person, where I stored the URL of the API and made a small function to show a summary of the person that was fetched from this person API. The function fetch does for us create a request instance. A reason we have to do it this way is for some reason the Python standard URL lib requests are blocked with a 403 by the API, so we have to send a custom user agent. Hence, I'm using this request object. Here it is the easiest to just use the headers argument to add a user agent that is custom. Once we have this request instance, we can use the URL open function, pass it the request, and it will do the request. We get a response back from that. And since the response instance is a file-like object, we can simply use a JSON load, and this way fetch returns us a decoded JSON directly. In the main, we call the API 50 times. We fetch a person, and then we print the summary of the person. And the main function is basically just timing the whole thing. So we run our code, and then we see how long it takes to do this in a blocking fashion. Let's go over to the Rust side. At the top, we use instant. Again, like in Python on the left, we have here the timing. So what we do here is we start the timing, and then we can print the elapsed time to know how long this ran. Then we have our loop that does the 50 times API call as we do in Python on the left. The only difference is we use the ureg get with the URL that is also in our module person as we created here in Python. Once we have that, we can use this builder pattern to set our custom user agent header. Once we have that, we can call it. Then we can call into JSON. And since we have not pre-coded any structs that would represent the person that is coming back from this API, we can use the 30 JSON's value type, and this will happily accept any JSON coming in, and we can actually fairly comfortably use that afterwards. I will show you once we look into the module of person. And then we do the same as in Python. We print a line with the person's summary, and we pass in the body that has actually already an instance of 30 JSON value. All right, let's run those two to see how long it takes and how a blocking API works. So on the left, we simply run the Python blocking code, and on the right, we can cargo run the same thing. We see that we get like a request every maybe half a second or something like that back. So this API is fairly slow. That's the problem with blocking, right? If you do stuff sequentially, you have to actually wait for the previous request to finish to do your next one. And you can see on the left and on the right, this took about 20 to 25 seconds. And that's fairly slow. If you want to get those data of these 50 persons, it would be better to improve on that. And this is why we have also the example of how we do this asynchronously. Now let's jump over into the code of the person. So what's the same in both is we have defined this URL to be the URL of the API backend. So in Python, you just use all caps to denote that this is more or less a static variable. In Rust, you will have to go. So it's a public static immutable variable that holds the string of the URL. And for the summary function, we can easily write this in Python, right? We just have an input called data. Then we know this is going to be a dict, and we know the structure of the person coming back from this API. So we directly want to go to the person's personal info, and then we can extract the person's name, last name, age, and country. To do the same in Rust, using the 30 JSON value, we would first pass a 30 JSON value into our summary function. So we have to define a data type. And this is actually fairly easy to use and very similar to Python, because you can see I just borrow data and get myself with the angular brackets person and the personal data out of it. So this is very close, those two lines. But then in order to access the keys inside of this JSON value, we have to be more precise in Rust, because if I access, for example, the name, I will have to convert it to a string and have to make sure that this actually, because this returns an option, because it can be a none, right? Maybe this name is not set within the JSON structure. So I have to also unwrap or otherwise handle this error. And that's why these lines are a bit longer, but generally they are very similar. So we can format and get those values out. Age is a number and not a string, so we don't have to use the as string in this case. Continuing further down, we can see here that we have this derive deserialize, and this is coming from the 30 derive up here. The reason for that is we want to be able to decode the JSON coming back from this getPerson API into a struct, or actually a nested set of structs. That will be possible with 30, and that's fairly easy to use. When we get in the data, it starts with a curly brace and has the first key called the person. So what we can do is we call a struct data in this case. We give this struct a property with the same name, so person. And this person is of type person. Next, we implement a struct called person. And the shortcut to not have to implement all those sub objects, I shortcutted and used education, for example, again to be a 30 JSON value. Same is true for those three. But for illustration purposes, I implemented the marriage subtype. So now we have our marriage struct. We can continue down here in the marriage struct. Let's hop over a bit lower in the code. So here we are pointing to the marriage struct, which is implemented here. And the person can be married, yes or no. This is a Boolean. And if they are married, they also hold info about how many children they have. So that's why usize. And if their spouse's name. Since the person can also not be married, so this is false. Those children and spouse name keys never show up in the JSON. That's why we have to use option. This makes this optional. So if children is missing or spouse name is missing, this is not a problem. And if they are here, then we get our usize and the string definition. And Surdy does the decoding for us into our data structure that we've created here. The cool part is once we have implemented data as our own data type, we can implement the display trait. And this way we don't have to use this summary function that we have written in Python here. We can use the standard formatting string, so those curly braces, to actually print our data object. So this maps the summary function that we've written before, but now it no longer uses the angular braces to access person and personal, because we have data person is a property and the personal is a property as well. And then we get to access as we did before with the 30 JSON in this case. How does this look in the Rust code? Let's quickly open up. So this is all auto done for us because all we had to do is, here we have one initial blocking call calling the URL, and we do the same thing. We call into JSON, but we here use the type hinting for person data instead of down here JSON value. So this into JSON automatically uses the 30 deserialized that we implemented for our struct to then give us this data thing. And then the print line data here just uses the standard formatter to use the display trait to print our data. So when we now run the application, we can see in the first line that this works. So let's run our Python code again and quickly cancel it. So this is the output, person colon is the output from our display trait, and it does the same thing, right? It gives the name, age, and country, and then below here we already have the start of our 50 times loop. Now that we've looked at our person module in Rust and in Python, we can now use this base type also directly in our asynchronous implementation. So let's open the source code for the async one. So for asynchronous Io in Python, we have the standard libraries async Io, and we use time again to time how long it takes now to do this in the asynchronous fashion. We had to install into our environment the AIO HTTP module. Once we have that, we can do the same as we did in our blocking version. From person we get the URL and our summary function. In order to fetch a single person, we will have to pass the session of our AIO HTTP thing and the URL. Once we have done that, this will then create us a response that we can await the JSON output of it, and then we can return that. In order to do this asynchronously, we also have to async define all the functions that we want to use. So we can await the fetch person and we can await our main. And we use the asynchronous context handler to get a client session out of AIO HTTP. We create a list of tasks. In this case, we also build 50 tasks. But the big difference is we don't wait for everyone to complete one after another. We only create the tasks here, or the futures. So async IO ensure future is we are making sure that fetch person is a future coming, and we pass in the session and the URL that we imported from a person. So we use afterwards the async IO gather, where we pass an iterable, in our case our list of tasks, and this gather will then go over the iterable and run in an async fashion all the tasks it finds, and if you await the result, it will return for every element in your iterable a list item with the result of the future that it awaited. This is very cool because you just write one line and your 50 requests are done basically in parallel for you, and they don't have to wait one another for the IO to happen. Once we have gathered all this information, we can loop over it, pass it to our summary function to get our printed output. And here we see the same code we had before. We time the main. This time we have to pass it to the async IO executor called run, our main function. And once this is done, we get our timing output. If we now run this, we will see that this is much faster than the more than 20 seconds we had before. So if we call Python async, it is done in well below under a second. The advantage of writing this asynchronous code is obvious. It's very easy to write, and there are already very many libraries implementing this gather type stuff, and of course different executors. Let's check out what happens if we look at the Rust code. So what I'm doing in Rust is I'm importing the join all, which is the equivalent more or less of this async IO gather. Then again, we need to have the person module loaded and accessible to get our URL and the summary function. And we use for timing the instant again. We have to tell the compiler that this will be an asynchronous thing, and Tokyo implemented for us already everything to start the executor and run everything. So all we have to do is add this line on top, define our main function to be asynchronous. The rest stays the same, right? We get still our result type and our errors. After that, we start the timer. So what we do here is we convert the range into an iterator. Then for every element in this iterator, we create a future from the create requests get function. We pass the URL. Now once we have done this, we can collect this into a vector of futures. These futures we can then join all. So this is the equivalent of the gather, and this iterator is the equivalent of this range loop. So join all futures creates a future that we have to await, and we can do that. This then also, as the gather does, returns us an iterable that holds the results of all the futures that it awaited. So we can loop over those. For every result that our request get produced, we are going to loop and try to print it. We can use from our person library the summary function. We pass it the p. The question mark makes sure that this is a valid result, because of course the result can fail for many reasons. For example, 404 code could be returned, or it is otherwise invalid. If this is the case, this question mark will actually exit and return an error on the main function. If everything is fine, we can use the request result Json function, and in order to get a 30 JSON value out of it, we define that in those pointy braces, and we await then the conversion into our JSON value. And if this fails, we use the question mark again to error out if there's a problem. Once we've done that, we've printed all the names in a nicely formatted debug fashion. And after that, we print the timing and we exit with an OK. Let's see if this is also fast as the Python version. So here we run the release version of the binary async that we created. And the runtime is in the similar, and the runtime is similarly fast. Here we will not see a speed difference between the two programming languages, because the slow part is of course the actual networking speed and talking to the other API, and not necessarily the code that we've written that runs on our powerful computer. I hope this gave a quick overview on how to write a simple blocking HTTP client, or when needed, to do many requests in parallel using the power of async programming to speed your processes up. And I hope it was also okay to go more in depth in what can be done using JSON in both programming languages. Thanks for watching. Coming up next on the From Python to Rust series will be HTTP servers.